Lesson: Fundamentals of Machine Learning and Neural Networks. Machine learning and neural networks are pivotal components in the broader field of artificial intelligence, significantly impacting how language models are built and refined. Understanding these fundamentals is crucial for professionals aiming to excel as certified prompt engineering professionals. This lesson focuses on actionable insights, practical tools, and frameworks that can be applied directly in real-world scenarios. Machine learning, at its core, involves teaching computers to learn from data and make predictions or decisions without being explicitly programmed. This learning process typically involves three types: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is akin to learning through examples where the model is trained on a labeled dataset. For instance, a spam filter is trained using emails labeled as spam or not spam, allowing it to predict the category of new emails. Practical tools such as scikit-learn, a Python library, facilitate supervised learning by providing efficient implementations of algorithms like linear regression, decision trees, and support vector machines. Scikit-learn's intuitive interface allows professionals to quickly prototype and evaluate models, making it indispensable in developing robust language models. Unsupervised learning, on the other hand, deals with unlabeled data, aiming to find hidden patterns or intrinsic structures. Clustering algorithms, such as k-means or hierarchical clustering, are popular choices for unsupervised learning. These algorithms can be implemented using tools like SciPy and NumPy, which are essential for handling numerical data in Python. A practical application is in customer segmentation, where businesses can group customers based on purchasing behavior, ultimately enhancing targeted marketing strategies. Reinforcement learning is distinct in that it focuses on learning optimal actions through trial and error, using rewards as feedback. This approach is highly effective in dynamic environments where explicit programming of every possible scenario is impractical. A remarkable example is AlphaGo, developed by DeepMind, which defeated human champions in the complex game of Go using reinforcement learning techniques. Libraries such as OpenAI Gym provide environments to develop and test reinforcement learning algorithms, offering a practical playground for professionals to experiment with these techniques. Neural networks, inspired by the human brain's structure, play a significant role in advancing machine learning capabilities, particularly in deep learning, a subset of machine learning. A neural network consists of layers of interconnected nodes or neurons, each layer transforming the input data to a more abstract representation. The power of neural networks lies in their ability to approximate complex functions, making them ideal for tasks such as image recognition, natural language processing, and speech recognition. Deep learning frameworks such as TensorFlow and PyTorch have revolutionized how neural networks are designed and deployed. TensorFlow, developed by Google Brain, provides comprehensive tools for building and training neural networks, offering flexibility for both research and production environments. PyTorch, popular for its dynamic computation graph, allows for more intuitive model building and debugging, which is particularly beneficial in research settings. For instance, BERT, a state-of-the-art language model, was developed using these frameworks to achieve unprecedented results in tasks like question answering and sentence prediction. A critical aspect of neural networks is their architecture, with various types tailored for specific tasks. Convolutional neural networks are designed for processing grid-like data, such as images, and have been instrumental in advancing computer vision. Recurrent neural networks, and their more advanced form, long short-term memory networks, are adept at handling sequential data, making them suitable for language models and time series forecasting. The concept of transfer learning, where a pre-trained model on a large dataset is fine-tuned on a smaller, task-specific dataset, has further enhanced the efficiency and effectiveness of neural networks. This approach not only reduces training time, but also improves model performance, as demonstrated by the use of pre-trained models in natural language processing. Addressing real-world challenges often requires a combination of these machine learning techniques and neural network architectures. For instance, in developing chatbots, a blend of natural language processing and reinforcement learning can create more interactive and adaptive dialogues, enhancing user experience. Furthermore, understanding the ethical implications and biases within AI models is crucial. Bias in training data can lead to skewed predictions, affecting fairness and equity in automated systems. Tools like IBM's AI Fairness 360 offer resources to detect and mitigate bias, promoting transparency and accountability in AI applications. To enhance proficiency in machine learning and neural networks, professionals should engage in continuous learning and experimentation. Online platforms such as Kaggle provide datasets and competitions that offer hands-on experience in solving real-world problems using machine learning techniques. Additionally, participating in open-source projects and contributing to libraries like TensorFlow and PyTorch can deepen understanding and foster innovation in the field. In conclusion, mastering the fundamentals of machine learning and neural networks is essential for professionals seeking to excel in AI and language models. By leveraging practical tools and frameworks and understanding diverse learning paradigms, professionals can develop more effective and ethical AI solutions. The integration of machine learning techniques with neural network architectures offers a powerful toolkit to address complex challenges and drive advancements in artificial intelligence. Continuous learning, experimentation, and ethical considerations remain paramount in navigating the evolving landscape of AI.